we'll start the second law here. So second law of this thermodynamics basically gives you about the direction of flow of heat. Okay. And in our textbook, it is based on the chapter. So we have seen in a previous chapter that first law basically talks about the total energy, and it talking about the total conservation of energy. So this means in first law, what we saw is that total amount of heat supplied, dq, is divided into two parts. One is the internal energy, other is the work. Okay, so dq is the heat supplied, du is the change in internal energy, and this dw is the total work done. Okay, so in this case, if we consider the first law, heat can flow if we have a ice at 0° ice, and we have is the 0° water. According to first law, heat can flow from ice to water. Okay, so this means it is possible in first law. Okay, but according to second law, if we consider the second law, we are talking to this point. Second law will basically telling that this is not possible. This will not possible. Okay, so let's talk about again the reversible process and the irreversible process. Okay, we are just repeating again. If we draw a graph of P and V, okay, so the initial state could be P1, P1, and T1, and final state could be P2, P2, and the temperature T2. Okay, so if we go from initial state to final state, okay, so P1, P1, T1 is the initial state, and P2, P2, T2 is the final state. So if we go from initial state to final state, and the question is here, if we go backward, final to initial, we are going through exactly same path. So initial path following the exactly same step, and when going from final to initial, it also follows the exactly same path. So this kind of process is called the reversible process. Okay, but if we are talking about the irreversible process, it depends on the path. Okay, so this is the main difference between the reversible process and the irreversible process. Okay, so let's talk about the heat engine. So heat engine is a device used to extract heat from a source and then convert, not completely, be careful about, partially into the mechanical work. Okay, that is used for all sort of the many sort of the applications. Okay, so for example, in simplest case, we can say that, say for example, we have this cylinder, and it has gas, some like this. Okay, and fitted with the piston. This is the piston one. So we can put this under the source. Source means we can heat from here. We can apply the heat. So if we apply the heat from the bottom, then if we supply the heat, then this at source, this behaves as a source. Source is generally at higher temperature. At higher temperature. Okay. The gas is actually doing the work. So two things could happen: work done by the gas or work done on the gas. So the gas inside the cylinder is called the working substance. Working substance, which basically expand, or means this gas could undergoes expansion, or it could go contraction. Means volume increase or volume could decrease. Okay, so this is called the working substance, and some of the heat is going in the atmosphere just outside. So in this case, if the extra heat that goes in the this region, like the atmospheric region, so outside is called this region. This region outside here is called the surroundings. Okay, this is the surroundings, this example. So this means if you supply heat Q1, then we applying the heat Q1, then this surrounding could receive the heat Q2. So Q1 is the heat supplied. This is the heat supplied to the system or to the engine. And what will happen that Q2 is basically the heat rejected to the sink. We call it sink. Rejected to the sink. Okay. So this outside, we also call the term is called the sink. So we are using the term source, sink, and the substance is the working substance. So in picture, the heat engine looks like this. So for example, this is the symbolic representation for the heat engine. So source is at higher temperature. This is the source, and this temperature is higher temperature, T1. T1 is the higher temperature. TH is greater than TC. So this is the sink. Okay. So this engine takes Q1 heat from the source, and it does work. This one work, external work. It do the external work W. Then it rejects the heat to the sink. At temperature TC. Okay. So this is the symbolic representation, systematic representation of any heat engine. So heat engine, basically what they do, they convert heat into the mechanical work, but not 100%. We'll come to this point. So heat engine, in this case, what they do is that they convert heat energy into the mechanical energy, means basically work. Okay. They convert heat energy into, but not completely, partially. Okay. So this is the symbolic representation for the heat engine. So based on this picture, we can write this in the equation form as our work W, external work done W, will be QH minus QC. Okay, this is the work. Okay, this is the work. So we can define the efficiency. Efficiency, I representing by symbol E here. This is the work done over the heat supplied, which will be QH. Okay, so we can use this equation to find the efficiency of any heat engine. Okay, So we can simplify further as E equals QH minus QC over QH. Okay, so this gives you E equals 1 minus QC over QH. Okay, QC over QH. And we can also write, if you want to write in percentage, just it is written as E equals 1 minus QC over QH times 100. Okay, so we can use either this equation to find the efficiency, or we can use in percentage these equations. Okay, so these all are in the equivalent form. So we so this is the expression for the to find the efficiency of the heat engine. Okay. Um, if you see in this example, the heat exhausted from the nuclear plant goes into the cooling towers, where it is released in the atmosphere. So here atmosphere behaves as a sink at lower temperature. So in simple word, source means at higher temperature, and if we talk about sink means where the extra heat will go. Okay, and so it's at lower temperature. So source and sink will be defined in this way. Okay, so let's talk about the heat pump. So the heat pump is also called the refrigerator. So what is difference between heat engine and heat pump? So you see here, here heat flows. If you see here, heat flows from sink. Be careful here. Sink to source means at lower temperature to higher temperature by doing with the help of external work. Okay, so here if you clearly see here, work is done. No, we have to work done on the engine. Okay, if you see in the previous example, this is the work done by the engine. Okay, this is the work done by engine, and here this is the work done on the engine. Okay, so just in the, if you write in the like a summary form, we can write as like this: in the engine, in heat engine, and we talk about the refrigerator. What will happen is this: in the case of heat engine, I put this symbol as for the engine. It takes heat from the source. Okay, then it rejects heat to the sink, then it does external work. Okay, so in this scenario, if you see, our value of QH is also positive. Okay, in this scenario, heat is going to reject, so we can take the symbol QC. Its symbol is the in this case value of QC is minus, negative, and work done in this scenario is plus. Okay, so I can write our equation as QH is basically equal to QC plus work W. Okay, so work W we can write as QH minus in term of symbol plus QC. We can also write this way, and this is equal to, if you talk about the positive value magnitude, QH minus QC. Okay, this is about the heat engine. If we talk about refrigerator, what will happen? This is the engine. And in this case, what will happen? We are applying the heat QC. We are doing the work done on the engine. It is work is this W, and the heat, total heat to the source will be QS. Okay, so in this case, the value you can write QH symbol is minus, and you can write QC it because heat is going inside the system, so it will be plus, and we can consider the work done on the system or on the engine, so its value will be minus. Okay, so similarly we can write QC minus W equals minus QH. Okay, minus QH. So other way around, we can write QC positive value plus work positive value equals minus QH. Okay, so that way we can write. So there's the difference between heat engine and the refrigerator. Let's do a little bit some math. So we can say that in the heat engine, heat engine, we defined efficiency. Okay, E equals work done over QH, so which was equals to 1 minus, if you write plus before the symbol, QC over QH. In terms of symbol, we can write as 1 minus QC positive value and QH positive value. Okay, for the refrigerator, we have to define the coefficient K, which is called the coefficient of, it has a name, is called coefficient of the performance. Okay, coefficient of this performance we define as QC over work. Okay, so this is, we can write as QC over QH, okay, minus QC. So that's how we can define the two term here. One is the efficiency, and the other for the refrigerator is the coefficient of performance. We can understand that way. Okay, so this is the actual is called the actual systematic diagram for this refrigerator. Okay, so based on this equation you can solve this problem. Okay, in this practice problem, some informations are given, means how much heat, 2.5 10 positive 14 joule of heat transfers from coal, and this much heat transfers into the environment, so you can find the total work done on the system. Okay,